Al-Muthna'na Governorate. Al-Muthna'na Governorate is located in the southern region of Iraq, about 282 kilometers south of Baghdad. It is divided into 4 municipalities, Al-Samawa, Al-Rumiatha, Al-Qudar, and Al-Salman, and consists of 7 sectors, Al-Warqa, Al-Majd, Al-Najmiya, Al-Hilal, Al-Daraji, Al-Sawara, and Al-Libsaya. The municipality of Al-Samawa received its name according to Yaqut al-Hamawi, since the land is extremely level and does not contain any kind of rock. One of the historical landmarks in Al-Samawi is Lake Sawa, which has religious importance to Muslims, for it is told that on the night of the birth of the Holy Prophet Muhammad, prayer and peace be upon him, the lake disappeared into the ground. Area and population. The border of Al-Muthna'na Governorate is 51,029 kilometers, which is the second largest governorate in area after Al-Anbar. According to local statistics for the year 1998, the population is 439,732, of which 215,190 are male and 224,542 female. World Bank Project. Financed by the World Bank's Iraq Trust Fund, the Iraq Municipality and Public Works signed a grant for the Emergency Water Supply and Sanitation and Urban Development Project to help restore basic water supply and sanitation services in the 9 governorates outside of Baghdad. Part of this grant went to the Muthna'na Governorate in order to improve the capacity and capability of providing fresh drinking water by upgrading the existing water treatment plant in the city of Al-Romaitha. After obtaining World Bank approval, a study of the proposed allocation of funds was necessary to prepare detailed designs for the project and provide a detailed implementation of the grant to the ministry. Here is a satellite image showing the existing water treatment plant and the proposed location of the new treatment works. The project consisted of upgrading the existing water station located on the shoulder of the Hela River in the province of Babylon, approximately 14.5 kilometers from the Euphrates River, with an identified construction site area of 8,500 square meters. The project consisted of, but not limited to, the construction of a conventional water treatment plant with a total capacity of about 40,000 cubic meters per day, comprised of the following units: intake structure and primary treatment system, low lift pumping station with a design flow of about 40,000 cubic meters per day and total design head of 10 to 12 meters, 2 coagulation, flocculation, and sedimentation tanks, each having a total capacity of 20,000 cubic meters per day and dimensions of 11 meters by 56 meters by 4 meters. A filtration building comprising of 8 gravity sand filters with dimensions of 27 meters by 45 meters by 6.5 meters. A chlorine contact tank comprised of 2 compartments, each one being 12 meters by 36 meters by 4.5 meters. A potable water high lift pump station, 19 meters by 12 meters. An electrical substation and generator, 18 meters by 12 meters. A chemical building, blowers and chlorination buildings, auxiliary facilities, and demolition of reinforced concrete structures. The ministry awarded the consulting services to Dar Al-Handasa, an international company with extensive experience in the preparation of engineering designs. They were responsible for preparing detailed designs and tender documents, along with the supervision and follow-up implementation of the selected construction company. Once Dar Al-Handasa finished the detailed design and prepared the technical specifications for the project, we submitted technical and financial documents under the pre-qualification process. Once we passed the pre-qualification process, the Ministry awarded the project to our company with an 18-month contract duration starting May 10, 2007. The following is the progress of work. Planning and follow-up by the head office in Amman, Jordan. Our company prepared a detailed timetable for the implementation of various items of the project using Primavera. Due to the vast numbers of buildings, tanks, and other components, and to ensure completion of the project within the contractual period, each part was considered separate from the other during the implementation phase based on the type of service the building provided. It was then handled according to the coherence and logical sequence of events for that building type. In order to streamline the project, our company implemented the principle of parallel action. Through this principle, our engineering staff prepared a detailed study of all technical specifications, including extracting the specifications for all civil and electromechanical materials by preparing detailed schedules of materials and equipment for the project. We then contacted every supplier for each article or intended basis and solicited both technical and financial detailed offers, which coincided with the technical specifications set by the consultant. After that process was finished, we conducted an engineering review to evaluate the proposals in terms of technical work and developed a short list of suppliers. Suppliers were then selected based on their offer price and technical capability. After reviewing all of the submittals, the final selection of subcontractors was submitted to Dar Al-Handasa for final approval. It is during this process that a letter of credit was opened to begin ordering supplies at the manufacturing stage and then delivery to the site. During this period, the site manager monitored the project and created daily reports which contained detailed images showing the development and progress of work, in addition to a brief narrative of the events that have been completed that day, events to be completed in the upcoming days, total staff working at the site, available materials, consumed material reports, equipment reports, and any problems or obstacles that impeded the progress of work. It was through these daily reports that a clear picture of the progress of the project was revealed, which allowed us to compare the progress of work against the planned time frame in order to take any necessary action to avoid delays. Configuration and creation of camps. The next segment of the project was the creation of our work site and the administration offices for the resident engineer and supervising consultant. These sites were equipped with all the stipulated contractual requirements such as furniture, equipment, offices, computers, and 3 2007 pickup trucks. In addition to the necessary camp facilities, we also constructed several warehouses and garages to store the equipment and cars necessary to implement the work. At the same time, in order to expedite the work and make most use of time, buildings were demolished and the rubble was excavated to areas identified by the municipality for waste disposal. Intake structure. The intake structure is approximately 30 meters long, 5 meters wide, and 3.5 meters deep. The main part of the tank was buried underground to allow the tank to fill by gravity flow. The design flow for the tank is 40,000 cubic meters per day to be discharged by 3 low lifting pumps, 2 running and 1 standby, each with a total head of 10 to 12 meters. In addition to the pumps, there are bar screen and band screens in the beginning and middle of the tank respectively. The minimum water level in the tank is 0.55 meters, and the maximum water level in the tank should not be more than 1.5 meters above the foundation level of the tank. Excavation work at the project site, which is located on the shoulder of the Hilla River, started on July 1, 2007. Due to differences in the level of several buildings, excavation ceased on July 7, 2007. After changing the point of reference levels, excavation continued on August 8, 2007 and completed on August 15, 2007. By the end of all excavation, approximately 500 cubic meters of sand was removed and transferred off-site. While this excavation was happening, we constructed a dewatering system to remove the groundwater that was filling the excavation area. Once the excavation was completed, approximately 50 cubic meters of heavy crushed rock was placed to serve as a drainage layer. After compaction and approval by the consultant, approximately 10 centimeters of blinding concrete was poured over the entire base with a quantity of approximately 45 cubic meters. The purpose of this was to provide a base for the steel bar work. Prior to installing the steel rebar, a waterproofing layer of EPDM sheet was laid. In parallel to the laying of this sheet, a cement sand screed was laid to protect the EPDM sheet from damage from rebar steel. After a period of curing the cement sand screed layer, steel rebar installation was started according to design specifications and drawings in order to provide casting for the concrete of the structure's foundation. Chlorine contact tank. An underground chlorine contact tank comprised of two compartments, each approximately 20 meters long, 38 meters wide, and 4.5 meters deep. The tank is attached to a high-lift potable water pump station that is approximately 22 meters by 12 meters. The clear well can store millions of gallons of clean drinking water. Filtered water undergoes a secondary disinfection stage when chlorine is added to the water to kill all the bacteria. 4 submersible pumps, 3 working and 1 standby, each with a 40-meter head pressure, are used to pump the water to the national water grid line. Another set of 3 submersible pumps, 2 working and 1 standby, are used for pumping water used to backwash the filters. For this portion of the project, excavation work began on August 16, 2007, with the removal of groundwater resulting from the excavation started on August 21, 2007. After completing the first stage of excavation to about 2.5 meters from the ground level, the remaining excavation was divided into 3 stages. This was done to control the process of groundwater levels, in addition to the maneuvering of equipment in an extremely limited space. On November 28, 2007, excavation work completed where some 12,500 cubic meters of earth were removed off-site. Once the excavation was completed, approximately 355 cubic meters of heavy crushed rock was placed to serve as a drainage layer. After compaction and consultant approval, approximately 10 centimeters of blinding concrete was poured over the entire base with a quantity of approximately 350 cubic meters to provide a base for the steel bar work. Prior to installing the steel rebar, a waterproofing layer of EPDM sheet was laid. In parallel to laying this sheet, a cement sand screed was laid to protect the EPDM sheet from damage from rebar steel. After a period of curing the cement sand screed layer, steel rebar installation was started according to design specifications and drawings in order to provide casting for the concrete of the structure's foundation. Sedimentation and flocculation tanks. 2 coagulation, flocculation, and sedimentation tanks, each 11 meters wide, 56 meters long, and 5 meters deep, were constructed. Each tank has a capacity of 20,000 cubic meters per day. The tanks collect the pumped water from the intake structure and discharge it to the filtration building. Chlorine and alum are added to the water on the flocculation side to kill bacteria and make the solid particles clump together. The clump particles then settle to the bottom of the sedimentation tank, where it is pumped out to the river by 6 mud pumps. Sludge scrapers scrape the settled particles to the end of the tank into the sedimentation pit. The remaining water flows over the end baffles, then into the filtration tank by gravity. Excavation work began on November 8, 2007, with dewatering systems in place almost immediately, and completed on December 12, 2007, removing a total of 4,500 cubic meters of excavated soil. Once the excavation was completed, approximately 355 cubic meters of heavy crushed rock was placed to serve as a drainage layer. After compaction and approval by the consultant, approximately 10 centimeters of blinding concrete was poured over the entire area, with a quantity of approximately 350 cubic meters. The purpose of this was to provide a base for the steel bar work. Prior to installing the steel rebar, a waterproofing layer of EPDM sheet was laid. In parallel to laying this sheet, a cement sand screed was laid to protect the EPDM sheet from damage from steel rebar. After a period of curing the cement sand screed layer, steel rebar installation was started according to design specifications and drawings in order to provide casting for the concrete of the structure's foundation. Service buildings. Chemical building. The chemical building housed the chlorine and alum systems. The chlorine is added to the water in the sedimentation and chlorine contact tank and the alum is added to the water in the flocculation tank. Both are controlled by systems located in the chemical building. Office building. An office building consisting of 4 offices, 1 archive room, a kitchen, an electrical room, and 2 bathrooms for plant personnel was constructed. Excavation work began on February 3, 2008, with dewatering systems in place almost immediately, and completed on March 4, 2008, with a total of 1,500 cubic meters of excavated soil. Once the excavation was completed, approximately 50 cubic meters of heavy crushed rock was placed to serve as a drainage layer. Once completed and approved by the consultant, approximately 10 centimeters of blinding concrete was poured over the entire base with a quantity of approximately 50 cubic meters. The purpose of this was to provide a base for the steel bar work. Prior to installing the steel rebar, a waterproofing layer of EPDM sheet was laid. In parallel to laying this sheet, a cement sand screed was laid to protect the EPDM sheet from damage from rebar steel. After a period of curing the cement sand screed layer, steel rebar installation was started according to design specifications and drawings in order to provide casting for the concrete of the structure's foundation.